Hello friends, I am Professor D.G. Trivedi going to take your third lecture related with the flip-flops. We have already studied about the flip-flop. What is a flip-flop? Flip-flop is a 1-bit memory device, and in a flip-flop it is a bistable electronic 1-bit memory device which is having a 2 inputs and 2 outputs. Both the output must be complement to each other. This is the definition of basic RS flip-flop, or it is called a latch. This basic RS flip-flop is called a transparent flip-flop because any changes at the input will directly reflect at the output. That means if you are having a set condition at the input, output Q will take the value of 1, and if you are having a reset condition at the input, then output is going to be 0, or it is going to be reset, or it will store 0 bit, and that's why it is called a 1-bit memory device. Here, the problem is this, that this flip-flop is always transparent. As long as the input is going to be changing, then output is also going to be responding accordingly. And that's why it is called a transparent flip-flop. The output Q will change the state immediately, provided that enable input is going to be high. This is called a gated or clock RS flip-flop. So we'll be starting with the age-triggered RS flip-flop. The simple latch type flip-flop presented in section 8.1 are completely transparent. That is, the output Q immediately follow any change of the state at the input. That is R, S or a D flip-flop. If it is RS flip-flop is there, if S is equal to 1, R is equal to 0, that is called set condition. The flip-flop is going to be set. And when R is equal to 1, S is equal to 0, then it is called a reset conditions. That means the output is going to be reset and it will take the value of 0. So this is the way it will change the state as soon as if you change the input state. Only time it will not change the state is 0, 0 conditions. If you provide that R is equal to 0, S is equal to 0, output is going to be retained or it is going to be stored. So this way, this flip-flop is known as a completely transparent. And that is the reason it was modified to gated or a clock flip-flop, because when the clock waveform is going to be low or the clock level is going to be low, then you can change the input, output is retained or it is going to be stored, output doesn't change. So you have the time that when you can change the inputs, that is when enable input is going to be low, the output can be stored, and when the enable input is going to be high, at that time output will be respond according to the input, and it behaves like a same as a basic RS flip-flop. So as long as the enable input remains high, the output is going to be changing and it is responding to the input changes, and that's why it is called a semi-transparent. The gated or clock RS and D flip-flop in section 8.2 might be considered as a semi-transparent. That is, the output Q will change the state immediately provided that the enable input is high. If any of these flip-flop are used in a synchronous system, care must be taken to ensure that all the flip-flop input changes state in synchronism with the clock. You know the clock waveforms, right? We have studied the clock waveforms. That means for certain period of time t1, it remains to be high. For certain period of time t2, it remains to be low. So t1 plus t2 is a periodic time of this clock waveforms. And as long as the flip-flop clock waveform is going to be high, it is remains to be enabled and you cannot change the input, otherwise output is also going to be changing. So either you have to keep this input constant or input level has to be fixed at constant or stable unchanging, while enable input is going to be high. When enable input is going to be low, you can change the input. This is the problem with the clock flip-flop or gated RS flip-flop. Both these problems can be overcome if we utilize the age-triggered flip-flops. If this flip-flop are used in a synchronous system, care must be taken to ensure that all the flip-flop input must change the state in synchronism with the clock. That means all the flip-flops inputs can be changed while clock is going to be low. When it is going to be high, it has to be maintained constant or fixed. One way of resolving the problem for gated flip-flop is to allow changes in R, S and D inputs level only when enable input is low, or require a fixed level at R, S and D anytime enable input is going to be high. At the very least, these are highly inconvenient restrictions, and at the worst, they may in fact be impossible to realize. So, this kind of limitation is very difficult or inconvenient restrictions are there. From the previous chapter, we know that virtually all digital systems operate in a synchronism mode. Thus, the age-triggered flip-flop was developed to overcome this rather severe restriction. So, there are two types of age-triggered flip-flop. That is, positive age-triggered flip-flop as well as negative age-triggered flip-flops are developed. So, how this can be done? You have the gated RS flip-flop. You have the clock RS flip-flop. So prior to the clock inputs, if you connect a positive pulse forming circuit, then it becomes a positive age triggered RS flip-flop. If you connect a negative pulse forming circuit, then negative age triggered RS flip-flop can be prepared. What is this pulse forming circuit? Pulse forming circuit we have studied in a previous semester. That means during the positive transition of the clock, small voltage spike or positive voltage spike as is going to be produced. So when the clock makes a transition from low to high, and that means at that brief instant of time only, the positive spike is going to be produced. That is called positive pulse forming circuit. Similarly, when the clock makes a transition from high to low, that means on a trailing edge of the clock pulse or falling edge of the clock pulse, for a brief instant of time, there is a pulse is going to be generated or pulse becomes low. That short period only. This is called negative pulse forming circuit. Positive pulse forming circuit is utilized to prepare a positive age triggered RS flip-flop, and negative pulse forming circuit should be utilized prior to the clock input of gated or clock RS flip-flop so that it converts into negative age triggered flip-flops. So in figure 8.18a, the clock C is applied to the positive pulse forming circuit discussed in section 7.1. The positive transition developed are then applied to the gated RS flip-flop. The result is a positive age triggered RS flip-flop with the IEEE symbol given in figure 8.18b. The small triangle inside the symbol, which is called dynamic input indicator, which indicates that Q can change the state only for this brief instant of time when the positive transition of the clock pulse will occur. Each positive transition of the clock in figure 8.18c produce a very narrow positive transition that is applied to the AND gate. The AND gates are active or enabled only while the positive transition is taking place or positive transition is going to be high. This duration may be around 25 nanoseconds only, and thus you can change the state only during this short in time period only. In this manner, Q changes the state in synchronism with the positive transition of the clock. This flip-flop is easy to use in any synchronous system. So, in this flip-flop, which can be utilized in synchronism with the positive transition of the clock in digital system or any computer system, etc. You can see that this is the logic circuit diagram of positive age triggered RS flip-flop. How it is going to be prepared? This is your basic RS flip-flop, which is having S and R are the inputs Q and Q bar is the output. So this is the logic symbol for a basic RS flip-flop. Prior to that, there are two AND gates are going to be utilized. These two AND gates, and it's one of the inputs are going to be common, and that will be utilized as a clock. Other two inputs is designated as S as well as R. So S and R are the control input which can set or reset this flip-flop, while enable input or clock input is going to be high. This is your gated flip-flops. And prior to that, if there is a positive pulse forming circuit is going to be introduced, that means clock pulse is given to the positive edge triggered circuit, positive pulse forming circuit, and output of that one is connected to the common input of both the AND gates. Then this is converted into positive edge triggered RS flip-flop. Similarly, if instead of positive pulse forming circuit, negative pulse forming circuit is going to be connected, then this flip-flop is going to be negative edge triggered clock RS flip-flop will be there. How it will function. But before that, let us see what is the IEEE symbol for that one. This flip-flop is having three inputs, S, clock as well as R. So these are the three inputs. Q and Q bar are output. Q bar is having a bubble which indicates that Q and Q bar are complement to each other. Moreover, for the clock, you can see that there is a small triangle inside this box is there. So there is a line and small triangle which indicate that this flip-flop is a positive edge triggered flip-flop. You can see the waveforms in a positive edge triggered RS flip-flop D. These are a clock waveforms which are perfectly periodic, and during this time its level remains high. During this time its level is going to remain high. It is perfectly a periodic frequency is going to be generated. When its clock frequency or clock levels is going to be changing from low level to high level, that is called positive transition or leading edge of the clock pulse. So on the leading edge of the clock pulse, there is a small voltage spike is going to be generated, and that small voltage spike duration may be less than 25 nanoseconds or something. And during that time only, the output of the pulse forming circuit is going to be high. So every leading edge of the clock pulse, this kind of positive pulses are going to be produced. So at time t0, at time t1, at time t2, at time t3, at time t4, this kind of positive voltage spikes are generated. That's why it is called a positive pulse forming circuit. Output of this positive pulse forming circuit is given to both the input of the AND gate. So these two AND gates are going to be enabled only while positive spike only. That means for a small narrow voltage spike only. Small interval of time less than 25 nanoseconds or something. At that time, whatever S and R inputs are there, either it is going to be set conditions or it is going to be reset conditions. If it is present at the other input of the AND gate, that input will be passed through the AND gate available to the basic RS flip-flop, and the basic RS flip-flop will be set or reset according to the input conditions, which is given in a truth table of figure C. That means if there is S is equal to 0, R is equal to 0, and if there is a positive voltage spike is going to be occur. Positive voltage spike is shown by this vertical upper direction arrow. And so when this is going to be occur, it is a no change conditions. That means output does not change. Output remains as the previous output. So Qn plus 1 will be like Qn only. If you are giving S is equal to 0, R is equal to 1, that is called reset conditions. So on a positive transition of the clock pulse, both the AND gates are going to be enabled, and R is 1 and S is going to be 0. So the flip-flop is going to be reset. So Qn plus 1 becomes 0. That is called reset. If S is equal to 1 and R is equal to 0, then for a positive transition of the clock pulse, the flip-flop is going to be set. So output Q becomes Qn plus 1 takes the value of 1, or it will store the value of 1. And if it is a 1-1 condition is there, both the outputs Q and Q bar is taking the same value, and hence it is a forbidden condition. So this way clock RS flip-flop can work. Another way to expressing its behavior is to say that the flip-flop is transparent only during the positive transition. It is not transparent for the remaining of the time. That means in a basic RS flip-flop is a completely transparent, 100% transparent. While gated flip-flop or clock RS flip-flop, when the clock level is going to be high, enable is going to be high, it is remains to be transparent. That means it will work as a semi-transparent. And in edge trigger flip-flop, only for a small interval of time, that is during the positive transition, which is less than 25 nanoseconds or something, the flip-flop is remains transparent. That means any change at the input R and S can reflect to the output Q. In other words, S and R inputs affect Q only while the positive pulse is going to be high. And they need to be static only during this very short interval of time. The truth table for the edge triggered RS flip-flop is given in the figure 8.18c. The small vertical arrow under the clock C means that changes of the state Q occur according to the R and S level, but only during the positive transition of the clock. Look at the waveform in figure 8.18d. Note that when Q changes the state, it does so in exact synchronization with the positive transition of the clock C. Now there is example related with this one. This example is 8.5. Use the positive edge triggered RS flip-flop truth table to explain the change in the Q or trace the waveform Q depending upon the input R, S and clock inputs with the time in figure 8.18d. Let us see the waveform itself now. So this is your waveform. So you know that now depending upon the S and R inputs, the output will change or it is going to be set or reset or no change conditions depending upon the value of S and R. So prior to the T0, if S is equal to 0, R is equal to 0 and we have started that initial condition, the flip-flop is already reset. That means Q is equal to 0. That condition we have taken. So when the time T is equal to T0 is there, T0 instead of time, depending upon S and R, S is equal to 0, R is equal to 0, so Q is going to be no change conditions. Q takes the previous value, Q was 0, it remains to be 0. Before the time T1, that means before the positive edge of the clock pulse occurs, second clock pulse occurs, at time T1, S is equal to 1, R is equal to 0, that means set condition is already presented. So when the positive edge of the clock pulse will occur, both the AND gates are going to be enabled and the flip-flop is going to be set. That means Q is changing from 0 to 1 at the stop time T1. At the stop time T2, S is equal to 0, R is equal to 0, 1. That means reset condition is present. So when the next positive edge is occur, the flip-flop is going to be reset. So the output Q will change from 1 to 0. Similarly, at the stop time T3, again S is equal to 1, R is equal to 0. That means set condition is present. So when this positive edge will occur, the flip-flop is going to be set and Q is going to be changing from 0 to 1. At the stop time T4, S is equal to 0, R is equal to 0. That means no change condition is present. So even if there is a positive edge is going to be occur at the stop time T is equal to T4, the output does not change. Output was 1, it remains to be 1 and Q remains to be 1 only. This is the way the behavior of the flip-flop we can explain. So the solutions, you can see that I have written the same thing here. Here what happens at each point in the time. Time T0, S is equal to 0, R is equal to 0. No change in the Q. Q remains 0. At time T1, S is equal to 1, R is equal to 0. That is set conditions. Q changes from 0 to 1. At time t2, S is equal to 0, R is equal to 1, Q resets. That means Q changes from 1 to 0. At time t3, S is equal to 1, R is equal to 0. Again, flip-flop is going to be set. Q sets to the value of 1. Time t4, S is equal to 0, R is equal to 0. No change condition is present. So Q remains into the previous state. That means Q remains to be 1. Notice that either R or S or both are allowed to change the state at any time while clock is high or low. That means this flip-flop is not responding to the level. When the level is steady, unchanging, either it is high or it is going to be low, flip-flop is not responding. This flip-flop is responding only while transition of the clock pulse. That means when the transition from low to high take place, that is positive age triggered flip-flop, and when the transition take place from high to low, that is negative age triggered flip-flop, and that's why it is called age triggered flip-flop. The only time both R and S must be stable, unchanging, is during the short period of positive transition of the clock pulse. Now we can discuss the same thing for the negative age triggered RS flip-flop. The similar way, prior to the gated RS flip-flop or clock RS flip-flop, you can utilize a negative pulse forming circuit to prepare a negative age triggered RS flip-flop. The symbol in the figure 8.19a is for negative age triggered RS flip-flop. The truth table in figure 8.19b shows that Q changes the state according to the R and S input, but only during negative transition of the clock. On the IEEE symbol, the small bubble on the clock input C means active low. This bubble along with the dynamic input indicator means negative age triggered flip-flops. So you can understand from IEEE symbol. Prior to the gated flip-flop, there is a negative pulse forming circuit is going to be utilized. And so in IEEE symbol, here there is a small indicator triangle which shows that it is age triggered flip-flop. Simultaneously with this bubble indicate that it is negative age triggered flip-flop is there. This flip-flop behaves exactly like the positive age triggered RS flip-flop, except that changes in the output Q are synchronized with the negative transition of the clock. Negative transition of the clock in a clock columns shown by vertical arrow, but it is in a downward directions, which shows that the actions will occur only while negative age of the clock pulse. Either it is going to be no change condition is there, or it is going to be reset conditions. Third condition is going to be set condition, or it is going to be forbidden conditions. So this is called negative age triggered flip-flop. The negative age triggered flip-flop, how it will be used for the same example of 8.5. Use the negative age triggered RS flip-flop to table to explain the Q changes of the state with time in figure 8.20. Here what happens at each point in the time. So that is shown here. Time t0, S is equal to 0, R is equal to 0. No change of the state will be there. So on the negative transition of the clock pulse, nothing is going to be happen. It remains to be reset. That means the previous value we have considered that initially Q was 0, so it remains to be 0. At time t is equal to t1, S is equal to 1, R is equal to 0. Q changes from 0 to 1. That means the flip-flop is going to be set on negative age of the pulse at time t is equal to t1. At time t is equal to t2, there is a reset condition is present. S is equal to 0, R is equal to 1. So the flip-flop is going to be reset and Q becomes 0. At time t3, S is equal to 1, R is equal to 0. Q again it is going to be set to be 1, and time t4, S is equal to 0, R is equal to 0. No change conditions. Q was 1 and it remains to be 1. So it remains to be high only. That can be shown in these examples. So you can see that these are the clock waveforms. Now every trailing edge of the clock pulse, or when the clock pulse is making a transition from high to low, this kind of negative voltage spike is going to be occur. So every negative edge of the clock pulse, there is a small negative voltage spike is going to be occur. That means normally this remains positive spike is going to be remains to be high, but for a brief instant of time it will go to the low state. That means for a brief instant of time less than 25 nanoseconds or something at T0, T1, T2, T3 and T4, these pulses are becomes low. That's why it is called negative pulse or negative pulse forming circuit. This can be introduced prior to the gated or clock RS flip-flop. And we have seen that how the output or the flip-flop will behave depending upon the input conditions, that is set and reset conditions. Notice that either R or S or both are allowed to change the state at any time, whether C is high, clock is high or low. The only time both R and S must stable, that is unchanging, is during the short negative transition of the clock pulse. Age-triggered D flip-flop. Although the D latch is used for temporary storage in electronic instrument, an even more popular kind of D flip-flop is used in digital computers and systems. This kind of flip-flop samples the data bit at a unique point in a time. That means at a unique point of time when there is a positive edge of the clock pulse occur, that time only whatever data is going to be presented, that data is transferred to the output, and that's why it is called this kind of flip-flop samples the data at unique point in the time in a delayed D flip-flop. This is again age triggered flip-flop. It can be either positive age triggered or negative age triggered D flip-flop can be prepared. In figure 8.21 shows that positive pulse forming circuit at the input of a D latch. The narrow positive pulse enables the AND gate for an instant. The effect is to activate the AND gates during the positive transition of the clock, which is equivalent to sampling the value of D for an instant. At this unique point in time, D and its complement hit the flip-flop inputs, forcing Q to set or reset unless Q is already equals the value of D, which we can explain in this circuitry. This is your basic RS flip-flop, and this is basic RS flip-flop with using the two AND gates. We can convert to the gated or clock RS flip-flops. Now S input and R input in between, we have introduced the inverter NOT gate. So converting to two instead of two data generator, two inputs, it is only one input, and that S is designated as the data input or D input will be there. So that way it is working as a D flip-flop. Now prior to this common terminal of both the AND gates, if there is a positive pulse forming circuit is going to be connected, this will work as a positive age triggered D flip-flop. How it will work? If we consider that okay, when the positive rising edge of the clock pulse will be there, that means leading edge of the clock pulse will be there, there is a positive voltage spike is going to be generated. That means that during this positive voltage spike, both the AND gates are going to be enabled, and whatever data is going to be presented here, that will pass through the upper AND gate and its complement will pass through the lower AND gate, and that's way either there is a set conditions or reset conditions is going to be occur for the basic RS flip-flop, and flip-flop is going to be set or reset depending upon the value of D. If D is equal to 0, or first consider the truth table here. That means there are two inputs. One is the clock input, another input is a D input, and this is output Qn plus 1. So if the clock input is going to be low, that means if there is no positive transition, if there is a clock waveform is either low or high, that means both the AND gates are going to be disabled. D cannot pass. S is equal to 0, R is equal to 0, no change conditions, so Q remains into the previous state. That means Qn plus 1 is equal to Qn. That means D can be anything, 0 or 1. It will not reflect in the output. Q does not change, so that no change conditions will take place. If we consider D is equal to 0, that means this input is going to be 0 and this input is going to be 1 because it is complemented by the inverter. So what happens? When there is a positive transition of the clock pulse will be there. This data inputs 0 and 1 will pass through the upper and lower AND gates available to the S and R. That means reset conditions will be there and the flip-flop is going to be reset on the positive transition of the clock pulse. Similarly, if D is going to be 1, that means the flip-flop is going to be set on positive transition of the clock pulse. So, which is shown here. That means output will take the value of D while clock is making a transition from low to high. So, every transition from low to high, the output is changes or output is going to be loaded with the inputs. Again, this operation is called ACE trigger because the flip-flop respond only when the clock is in a transition between its two voltage states. The triggering in the figure 8.21 occurs on the positive going edge of the clock. This is why it's referred to as positive edge triggered flip-flop. The truth table in figure 821b summarizes the action of positive edge triggered D flip-flop. When the clock is low, D's don't care and Q is latched in its last state. That means Q does not change. On the leading edge of the clock pulse, that is positive transition designated by the up arrow, data bit is loaded into the flip-flop and Q takes on the value of D. When power is first applied, the flip-flops comes up into the random state. That means output of the flip-flop can be latched either 0 or 1. That is randomly depends. So to get some computer started, an operator has to push a reset button. This sends a clear or reset signal to all the flip-flop and all the flip-flop output is starting with the initial value Q is going to be 0, 0, 0. Also, it's necessary in some digital system to preset synchronize with the certain flip-flop. So sometimes it is required that all the flip-flops are starting initially with the preset. That means the Q should be 1 for all the flip-flop and that is also one of the important things for the initial conditions. So either all the flip-flop should be reset or all the flip-flop should be set and that kind of arrangement is required. Figure 8.22 shows how to include both these functions in a D flip-flop. The edge triggering is the same as previously described. Here there are two OR gates which are inserted here after this AND gate and prior to the basic RS flip-flop. So basic RS flip-flop is operating with the preset terminal as well as clear terminal. If the preset terminal is going to be high, output of this OR gate is going to be high and clear terminal is low, so at that time R is going to be 0 and the flip-flop is working as a basic RS flip-flop, so flip-flop is going to be set. So when the preset terminal is going to be high or it is called active high, that means the flip-flop is going to be set, and when the clear terminal is going to be high, output of this OR gate is going to be high, R becomes high, S is going to be 0, flip-flop is going to be reset or Q becomes 0. So that way the flip-flop preset and clear are active high here and they are called asynchronous control because without bothering the clock pulse or it is independent of the clock pulse, this inputs, this preset and clear inputs can directly control the flip-flop and that's why it is called asynchronous control. It can preset or it can clear depending upon what input you are giving at that inputs. Here there is a reset button is there. So if the reset button is open, this input is going to be 0. So D input is passing through this OR gate and every clock positive transition of the clock pulse, the D input is transferred to the output or the flip-flop is going to be set or reset depending upon the D input. If D is going to be 1, the flip-flop is going to be set and D input is going to be 0 on positive transition of the clock pulse, the flip-flop is going to be reset. Depressing the reset button will set Q2 equal to 1 with the first positive transition of the clock pulse. Q will remain high as long as the button is held close. The first positive transition of the clock after releasing the button will set Q according to the day input. Furthermore, the OR gate allows us to slip in a high preset or a high clear when desired. A high preset force Q2 equal to 1. That means the flip-flop is going to be preset or it is going to be set. A high clear reset the flip-flop. That means Q becomes 0. The preset and clear are called asynchronous input because they activate the flip-flop independently of the clock pulse. So without clock pulse, this input can control the flip-flop. That's why it is called asynchronous inputs. On the other hand, D input is a synchronous input because it has an effect only with positive transition of the clock pulse. So the input D, whether it can set or reset the flip-flop, but after the positive transition of the clock pulse occur. That's why it is known as a synchronous input. Figure 8.23a is IEEE symbol for a positive edge triggered D flip-flop. The clock input has a small triangle to serve as a reminder of edge triggering. When you see this symbol, remember what it means. The day input is sampled and stored on a positive transition of the clock pulse. Sometimes triggering or negative transition of the clock is better suited for the application, and that's why negative edge triggered D flip-flop can also be prepared. In this case, an internal inverter can complement the clock pulse before it reaches to the AND gate. So inside the IC there will be an inverter will be there. So when the negative pulse forming circuit is given, that means when the negative transition of the clock pulse occur, that time internal inverter will convert into the positive edge and it will respond actually on the negative edge of the clock pulse, and that way the negative edge triggered D flip-flop can be prepared. Figure 8.23b is the symbol for the negative edge triggered D flip-flop. The bubble and triangle symbolize the negative edge triggering. Figure 8.23c is another commercially available D type of the flip-flop, the IC 5474175 or IC 5474 LS175 low power Schottky TTL are having 4 D type. This edge triggered D flip-flop is available. Besides having a positive edge triggering, it has inverted clear input. This means that a low clear resets it. That means when this clear input is going to be activated, the flip-flop is going to be reset. That means Q becomes 0 and Q bar becomes 1. Besides having a positive edge triggering, it has inverted clear input. This means that a low clear reset it. The 5474175 has 4 of this D flip-flop in a single 16-pin dual in-line package DIP, and it's referred to as quad D-type flip-flop with a clear. So these are the various symbols for D type of flip-flop. Normal positive edge triggered D flip-flop, which is having a 2 inputs, D input, straight line, and edge triggered. That means there is a small triangle and line which indicates that this is positive edge triggered D flip-flop. Here data input line as well as there is a small triangle and bubble which indicates this is a negative edge triggered D flip-flop. And here there is a D inputs positive edge triggered D flip-flop, and you can see that there is a clear input is also there with bubble which indicate that it is active low, clear input is there. So this terminal is going to be activated, the flip-flop is going to be clear or it is going to be reset. These are certain questions related with this topic. What does it mean to say that a flip-flop is transparent? Second question, what is positive edge triggering? Third question, what does an RS latch differ from edge triggering RS flip-flop? The clock input to the D flip-flop in figure 8.21 is held low. What effect does the D input have? And the last question, to preset the flip-flop in figure 8.22, what level is required at the preset input? what is the resulting state of the output Q1. So these are the questions you have to understand and you have to answer, because I'm not answering because I want to check whether you understand these things or not. Okay, thank you very much, friends.